This industrial robotic arm is executing a pick-and-place operation with surgical precision. In under 6 minutes, Royal Research will show you how to build this exact simulation from scratch, allowing you to test your production logic before spending a cent on physical hardware. To follow along, you only need the RoboDK software and a single 3D CAD file of your workspace, such as a step file, an IGES file, or an STL file. Even if you have never programmed a robot, you can complete this. You do not need any prior coding knowledge or access to a physical robot to get results. Modern simulation tools bring high-level engineering to a standard desktop interface, allowing any creator to design and test complex assembly lines from their own workstation. The RoboDK interface has 3 primary zones: the toolbar for commands, the tree view for project management, and the 3D view for real-time visualization. This tree view is your project's hierarchy. Every 3D object is managed through this list. To add your first component, right-click inside the tree view and select Add Robot. You can then browse the manufacturer library to find exact models from brands like ABB, KUKA, or FANUC, filtering by reach or payload capacity. Once selected from the library, the digital model of the robot spawns directly into the center of the 3D view. At this stage, you must open the Parameters panel to verify the robot's dimensions and joint limits. This ensures the digital twin behaves exactly like the hardware it represents. Taking a moment to verify these specs now prevents the simulation from attempting movements that are physically impossible for the real-world machine. Next, we add the environment. You can drag and drop your workstation's CAD files, like a STEP or STL, directly into the 3D space. RoboDK automatically positions this imported environment relative to the robot space, creating the physical stage for the operation. We then establish frames. These are spatial reference points that tell the robot where objects are located within the room. To interact with the world, we add a tool, like a gripper, establishing a tool center point. Ensure you input its precise dimensions. If off, the software miscalculates clearances, causing undetected collisions. Defining these frames and tools accurately is the specific step that transforms a simple 3D model into a mathematically reliable simulation. Now we program the movement using targets. These are the specific coordinates in space the robot is required to reach. Position the robot arm manually in the 3D space and lock in the coordinate to create your first waypoint. Repeat this for every stage, creating a series of targets that define the robot's path. You can then organize these targets in the tree view, dragging them into a sequence to form a continuous, logical movement loop. Use the graphical programming tool to link these targets into a final executable script. Then press play. While running the simulation, activate the collision detection feature. This tool ensures the arm doesn't strike the workstation or itself. If you see a collision, pause the playback and adjust the target coordinates in the tree view until the path is clear. Refining the path in this virtual space allows you to catch and fix hardware-destroying errors before you ever power on the actual robot. This is the final result you will see: a completely functional pick-and-place operation running on a reliable, error-free loop. This completed simulation provides immediate data, allowing you to estimate cycle times and production capacity with a high degree of accuracy. From here, you can expand the project by integrating Python scripts for custom logic or connecting to CAM software for complex manufacturing paths. On behalf of Royal Research, thank you for following this guide. Building a digital twin allows you to solve the most expensive problems, like timing errors and physical collisions, well before your robot ever arrives on the factory floor.